Tonight's speaker, David Jewitt, is a professor at UCLA. He got his bachelor's degree at the University of London in 1979. Then he came across some big water and got some more degrees at Caltech. Then he was a professor at MIT and then at the University of Hawaii. And just last year, he came back across some more water back to UCLA. He is the recipient of the Exceptional Scientific Achievement Award from NASA. He is a member of the American Academy of Arts and Sciences, the American Association for the Advancement of Science, and a member of the National Academy of Sciences. So we are very pleased and fortunate to have David here tonight. So thank you. Good luck.
That's scary. Thank you very much. Let me first apologize for my voice, which is strained by a previous talk I gave today, and by talking to people all day from like 9 o'clock this morning. So my voice is a bit burned out. And if you can't hear me, do something to tell me that, okay? And I'll try to speak louder or something. Let me echo the first remarks about the importance of public education in science. You know that this country has a crisis at the present time in that people, basically young people, are not going into the physical sciences where you need mathematics to do much for all sorts of reasons, but the main reason is they're hard. And so the way to combat that surely is through programs like this and other ways to reach out to young people and tell them what's going on and why it's exciting and why it's worth doing a really, really hard thing instead of doing easier things that are often more lucrative than the physical sciences. So I'm very supportive. I'm here because it's a good idea. I'm happy to be here. I think this probably should be a very interactive event to be effective. Am I right? Yeah. So please ask me questions as we go along. I don't want to talk too much for all sorts of reasons, one of which is my throat, but I think the questions are the real way for you to control what I say and to steer this discussion. I thought the planning for this talk is in 3 parts. First of all, I thought I would introduce what it's like to do modern astronomy, just give you a picture of what actually people like me do. Second of all, try to give you an overview of the solar system. So we have this new view of the solar system that's emerged in the last 20 years or so. I'll just give you a flavor of what that is and why we think that's exciting. And then a particular issue at the bottom, the third one, is to discuss the origin of the oceans. So it's a nice subject because it connects the study of the sky with the study of the Earth and things on the Earth. And you know, I'll try to stop all the way through and encourage questions. And if you don't have any questions, I'll assume that my talk is a dismal failure. And I'll leave kind of sad. So, modern astronomy. So the old idea is that, you know, the astronomer is some guy, probably bald, probably with white hair, who has his eye stuck to the bottom end of a telescope all the time. And that nothing is further from the truth. Well, sometimes astronomers are bald, and sometimes their hair is beginning to go gray, but we almost never look through telescopes now because we have detectors that are much, much more powerful than our eyes. So we can see much more with electronic cameras than we can see just by looking through a telescope. And we get a permanent record basically by taking pictures that we don't get when we look through by eye. So, could we have the lights off? Ooh, yeah. Could we have the lights off?
That's your first question.
That was a good question. And I hope the answer is yes. So where do we go? Well, for many, many problems, astronomical problems, the issue is how to see through the Earth's atmosphere clearly. And you might say, well, you know, just wait for a clear night. But that's not necessarily enough. So we like to have clear skies. So we need to go to places where the sky is clear most of the time. I think the sound just faded or died. That's okay. Oh, okay. I'll talk as loudly as I can without causing a sound explosion. So we go to high places because it's frequently clear above mountains. If you pick the right mountains, you can have good clear skies a lot of the time. But the other reason is that we need to get above the water vapor in the atmosphere. So water vapor makes clouds, but even when you can't see the clouds, the water vapor is still there. And the water vapor absorbs some of the wavelengths, some of the light that you would like to detect from the ground. So you could say, well, why even do astronomy from the ground? Why not just go into space? You know, we've got a space telescope. Why not just use that? And it's true. Space would be the best place to go for basically every kind of astronomy. But space is very hard to work in. It's hard to get there. It's super expensive. And when you're there, there's not much flexibility. It's hard to fix your telescope. It's hard to do anything in space. So it's still not practical to do most of what we want to do in the space environment. Island of Hawaii. And on the top are various telescopes from different countries all around the world that go there to take advantage of the high site and the dry site that is Mauna Kea. So here, just to show you what it's like, is a picture from a couple of years ago that I took while I was observing. This is a view from Mauna Kea. It's a 4-kilometer high volcano, 4,000 meters. And looking to the south is a similar volcano. This one is called Mauna Loa. The one we're on is called Mauna Kea. And in the foreground is a cone called Goodrich Cone. Everything here is volcanic. This is all lava squeezed up from beneath the Earth's crust in the last million years. Goodrich Cone is named after an English explorer person who came to Hawaii on a whaling ship and one day decided to walk up to the top of the island from the coast. He landed in near Waimea and just started walking. This is a tremendously difficult walk. It's rough. The ground is very, very rough. His shoes were not that good. And as you know, you go up and it gets colder. So he found that the higher he went, the colder he got, and the more bleak the conditions became. So about 10,000 feet, all the plants disappear, and it's just rock. And then about 12,000 feet, it's snow and rock. And he came all the way up to the top of this crater, and he found it was full of dead sheep that had wandered up the hill and became disoriented from the lack of oxygen. So the pressure is 1/3 less than the pressure at sea level. And they also became dehydrated because there was no water for them to access. And they also froze and died in the summit of this crater. Now, almost the same thing happened to him. He only brought one small blanket with him. So, and he couldn't get down in time for the night. He found a small hole in the cinder cones inside Goodrich Crater. He got down inside the hole, covered himself with a blanket, and almost froze to death that night. And then when he survived, he walked up, staggered down the mountain back to Waimea, and told everybody, do not go there. That is hell on earth. That is the worst place you would ever go. And nobody went there. No white people went there for several decades after that, based on his first recommendations of what it's like. So not a very comfortable place for, even today, not a very comfortable place for astronomers. You have a headache, you feel bad, you get dehydrated, you always lose weight. My wedding ring, which does not come off, up there just falls off. It falls on the floor because of weight loss, because of loss of water from my body. So it's basically a place where you feel that your body is decaying day by day as you stay up there. But it's a really good place for astronomy precisely for those reasons. You're above the water. You're above the water vapor. You look down, you can see the clouds are below us. It's like looking through an airplane window, but there's no window. It's just in front of you. And so it's a fantastic place for astronomy for that very reason. And here are some of the telescopes that we like to use. We like to use these ones because they're the biggest ones in the world. So in astronomy, the bigger the telescope, by and large, the better, because you collect more light. So the starlight is very, very faint, The bigger the mirror, the more light you can collect. This one is, these are each 10 meters in diameter. So, 34 feet in diameter. The mirrors, the domes are much bigger, 100 feet. And this is a Japanese telescope, slightly smaller, but very good in its own way. So we go up to the top of high mountains and suffer the conditions up there because it's really good for astronomy. So I have this movie that shows 24 hours at the summit of Mauna Kea, just to get you somehow involved in the feeling of what it's like to be up there. And the big deal is that we're so high that the clouds, the water vapor boils up from the ocean and comes up to a level where it condenses as water and then goes back down. So you'll see a boiling cloud layer beneath us, and nothing comes up above the top of the clouds. So this is a nighttime picture. Here are stars going up to the upper right on this picture. Here are clouds down below. This is the outline of the volcano below us right here. There's a planet, and here comes the sun. So here's sunrise. Now you can see the sun shining on the cloud deck here, and the cloud deck is boiling and starting to puff up because as it gets warm, it puffs up and becomes thicker. And it begins to approach the camera, which is on the top of the volcano, 14,000 feet above sea level. Here come the clouds. They almost get to the telescope. And then the sun goes through the meridian. It's becoming afternoon and starts to go back down. Here comes the shadow of the dome. The shadow goes out across, up the sky. That was the shadow of the Earth passing by. And then it's nighttime. And then stars rise. In a moment, the moon comes up. And then you can see the clouds boiling in the background again. So actually, you can stand outside, if you're not using the telescope, and see all this with your eye. And it's just as fantastic as the movie, but more so because you're right there. It's real. It's just amazing. Another thing I can tell you about but can't really show you is, for example, the wind. So the wind at that altitude is astonishing. You can have, and I've had many times, you can have an observing run of a week on Mauna Kea where the wind comes at you at, say, 50 miles an hour. So you go up there. It's too windy to open the dome, so you go outside to see what the conditions are like. 50-mile-an-hour wind comes towards you from the east at sunset. It's still 50 miles an hour at midnight. It's still 50 miles an hour at sunrise when you go back down again to sleep at a lower altitude. It's 50 miles an hour from the same direction when you come up the next night, and it goes on for several days like that. So you can have a wind 50 miles an hour going for almost 100 hours. So it goes for thousands of miles across the Pacific at this constant and tremendous rate. So it's a very, very exciting, even if you don't care about stars, it's a very exciting meteorological place to go. Did you have a question? Yeah. Cool. It's convection. So the sun heats, the sun is absorbed by the ocean or by the land if the land is in the way. And when you heat something from the bottom, it's like heating a pan of water. It sets up a boiling motion. So it tends to rise and carries the heat from the surface upwards. And in this case, it goes up to this particular level. It's called the inversion layer, where basically it's a cap to the convection. So it's ultimately the heat from the sun. So if there were no sun, that would be really bad from many perspectives. But it would be good in terms of keeping the clouds down. Yeah. So it's like on a hot day in the summer, you see these big cumulus convection clouds that rise up. That's simply a convection cell that will go away at nighttime. The things that just rained on us actually are the same kind of cloud. They're convection columns caused by heating of the sun on the wet ground. So that was just a quick intro to what it's like to do modern astronomy. Yeah, oh, sorry, there's a question in the back, and then a question in the front.
How do you get up and down, and how are you supplied? Roads, helicopters?
So there's a road that was put in about 1970-something by a person with a bulldozer. And now it's better. It's a paved road. In part, it's paved. We don't sleep at the summit, basically because it's too high. So 14,000 feet, you just don't feel good. You can't sleep much, and it's just not, you dehydrate, all the rest of it. We come down to a base camp called Halipahaku, which means House of Stone, which is about 9,500 1,000 feet above sea level, so it's much, much better. You have more oxygen and more humidity. And we sleep there. And actually it's quite nice. It's a nice building, not as nice as this one, but a nice building, and there are cooks, and they make food for you. There's a kitchen, there are computers, all sorts of goodies at that level. And we go up and down by a four-wheel drive vehicle on this road. It's about a 10-mile journey from Haleʻipahaku to the summit horizontally, and it's about 1 mile vertically, roughly. So it's a 1 in 10 road, and bumpy and dusty and the whole thing. Yeah. So you had a question?
Well, I was going to ask about the road, but I was also curious, does it affect the vehicles going up and down?
Yeah, they fall apart. Yeah, the vehicles literally fall apart. So my favorite one is the Subaru, like the big Subaru, but also the Chevy Suburban is a really nice, strong car. But the typical thing is that the hood just shakes off. Just shakes off. That's what happens. Just they fall apart. So they don't last that long. Yeah. Yeah, it's a public road, so in principle you can just drive up. In practice, if you go to Hawaii and rent a car, they have legal language saying, "Don't go up there. Don't go. It's gonna damage the car." But you can do it. I've driven rental cars up there many times. Sometimes with bad results, but usually it's okay. Yeah. So sometimes people make TV programs, Nova programs, and so on. Oh, another question. Yeah.
Well, since we're on the topic,
That's good.
mountaintop,
Yeah.
what's the weather like there? Are there seasons? Is it snow at times, or is that attitude always?
Yeah, it's seasonal. The average temperature is close to freezing, so it's basically never very far from freezing. It does vary seasonally, but only by a few degrees. It varies in the day, day to night. Diurnal variation is also maybe 10 degrees, something like that, sometimes 20. And usually a little above freezing in the daytime because of ground heating by the sun, and a little below freezing at nighttime. Beneath the ground is permafrost. So snow that falls eventually melts and then seeps down into the porous volcanic soil and freezes. And so there are these big plugs of ice beneath the surface, which you don't see because of the porous cinder cones on top. Nothing lives there except for one bug called a wekiu bug. And you might say, well, if nothing lives there except for one bug, what does it eat? Is it cannibalistic? The answer is no. It eats the bodies of other bugs that are blown up from sea level by the strong winds. So it literally is this funny-looking spider thing that hangs upside down under rocks on the summit, waiting for the body of some dead insect to fall nearby. And then in the near freezing temperatures, insects don't work very well at such low temperatures. It creeps over. It's got antifreeze in its blood. It creeps over and eats the carcass of this thing that blew up from sea level. That's a very specialized little bug. Yeah, but they probably like astronomers because astronomers drop food over the edge of the telescope, and it's like a food bonanza. Anyway, so TV companies like to think they want to make movies of astronomers at work, because they have in their heads this idea that you're out there with a big telescope looking through the eyepiece, and it's going to be kind of cool and dramatic. And when people ask me about that, I always say, well, it's not the way you think. It's really kind of boring to look at by comparison. We mostly use computers. We use a computer to control an instrument attached to a telescope. We don't look through the telescope. We're usually in a room because it's so cold outside. We don't want to go outside. We're scared of the low temperatures and no oxygen. And they say, yeah, but we'd really like to make a movie of this anyway. And then they come out. So I made this movie myself while I was observing on the Keck telescope. It's the world's biggest telescope, just to show people ahead of time what they will get if they come out and waste all their money with the big TV cameras to make a movie of this. So I'm going to show you this movie, and this is about as realistic as it gets. So we're in the control room of the Keck telescope, but this control room is not at the summit because it's so unpleasant up there. It's been moved to this town, Waimea, which is down at about 6,000 feet. So we're in a nice room. Outside is a nice evening, the whole thing. We're very comfortable by comparison. Here's what we do. So we're using these computers here. This is Pedro Lacerda, who was my postdoc, he's from Portugal, he's now back in Ireland. We're using these computers to control cameras on the Keck telescope about 25 miles away and 2 miles above us in this picture. And we're looking at the data as it comes down. We're jumping around. We're active because we want to make sure the quality of the data is good. I'm looking at a picture that was taken from the camera right there. We get hungry. We go out and we come back in a little while, I think, with some food. There you go, there's the apple. Pedro is drinking. Pedro does something on the floor, I don't know what. We have a conversation. We get a little bit cold. Come back with a coat. And this just goes on hour after hour after hour, as long as it's clear. So typically, 10 or 12 hours per day. So that's actually what astronomy looks like. And you don't see that on TV because it's not really what people expect. Yeah. But it's what you have to do. So if you're interested in doing science, then you have to get observations. You just have to take data in order to understand the physical world. And the only way to do that is by this kind of a crazy dance, really, at the telescope.
How do the computers work up there? They get frozen?
No, the computers don't get frozen. The main problem, the two problems. One is, the question was, how do computers work at high altitude? There are two problems. One is transporting the computers or any other sensitive equipment up to the top is a little bit risky because of the bumps. So many computers die, usually the disk dies, because of vigorous shaking in the car going up. The same thing that destroys the Suburban also destroys a computer. And then there is some pressure effect. No, if you, like this computer, for example, which I've taken to the summit many times, actually is not guaranteed to work above 10,000 or something, 10,000 feet. So we go significantly above that. And some computers, for reasons which I don't understand, simply die up there. And so you don't take those computers up there again. You bring them down and fix them and take up another one. Yeah. So some computers don't work well at high altitude. Yeah, another question.
I would imagine that scheduling in time of these big telescopes is rather valuable. What
Yeah.
percentage of your time do you spend actually observing and collecting data
Yeah.
versus the astrophysical analysis?
Very small, very, very small. So the Keck telescope, this one right here, has an operating cost, which is, let me just see, I think for this particular telescope, it's between 10 and 15,000 per night, something like that. So most of the money goes basically to pay a huge army of people, experts, who keep it working, because any complicated technological thing just spontaneously falls apart. So it needs people to keep it going, like your car, but at a much higher rate. So people think it's very valuable. The most expensive telescope scared me too. The most expensive telescope is the Japanese one, which is $80,000 per night. Because of the way the Japanese operate their telescope, they have a very huge army of people and connected to very expensive companies back in Japan. And so in fact, those companies make a large profit from the operation of the telescope, which is not true for a Keck, which is a private telescope. So it's a much more efficient business. So the allocation of time is determined on the basis of proposal. So we write a proposal that's judged by other astronomers. So you have to make a case that the measurement you want to do is worth allocating the time on the telescope. And typically you would get a block of a few nights in a row for any particular telescope that you want. So on Keck, it's usually 2 nights in a row, or sometimes 3 if you're lucky. But not much more than that because the competition is pretty high for that. But world's biggest telescope, you can do a lot in a relatively short amount of time. How much time per year? So when I was in Hawaii, I was totally nuts. I went completely crazy for most of the last 20 years. And I would observe probably for between 1 and 1.5 months per year, something like that. So I'd be up there for about 10% of my life, which is far too much. And look at me now, if I I'm only 25 years old, So depending on the kind of measurement that you take, you don't need anything like that amount of time. It depends on the particular science and so on. But if you do any leading edge measurements, then you need quite a bit of time. But it's a small fraction of the total year. So most of the year, I would just work in a regular university and then go up to the summit for a small number of nights per year. Yeah. Okay.
Are you sharing your information between satellite, between these observatories?
No.
The Japanese people, they say we found something, you guys look at it too?
No. No. Why did you mention the Japanese? No. So it's competitive. So, the science is basically conducted in a competitive spirit, which is good because it makes it go fast and go far. And the way of sharing results is through publication. So you basically share things by writing carefully reasoned papers about them. Instead of finding something and then giving everybody a phone call, hey, I found something cool, you go through the whole process and write a paper about it. And most people are not happy about giving away their best results until they've reached that stage of publication. So the metric of productivity in science is the paper, scientific publication. And so people want to save it up and then have a good paper, typically. There are a few cases where that's not so, a few cases where something amazing happens, and if you don't observe it in the next day, it'll be gone. And then people will just ask for help, basically. Yeah, so it does happen. So it's competitive, it's usually friendly competition, which is a good circumstance, yeah.
Why even go to Hawaii? Why not just do it remotely completely?
Yeah, it's better. So the people who operate telescopes increasingly try to move astronomers away from telescopes, which from a managerial point of view makes sense because you don't have to support the people, they don't have to travel, you don't have to show them details of the instrument at high altitude. It's just more convenient. But, many of us think that that's actually not a good thing because it really sucks the fun out of astronomy. So many people became astronomers because something happened when they were children and they got excited about the sky. And the thing that's exciting is you can look at it with your eye or a pair of binoculars or something. You can just do it. And so the further removed you are from that process, to me and many other people, the less exciting it is. So there is this move to kind of bureaucratize astronomy and separate astronomers from the thing that they should be doing in the interest of either saving money or making it more efficient, whatever that means. But, how efficient is it if the people doing the research are not so excited about it because they're taken out of the picture? So I think it's a very destructive process, but it is happening. So Keck, for example, we used to always go to the summit, and it's painful, and your nose dries out, you get nosebleeds, and everything hurts. But actually, it's kind of exciting to be up there, and you can really see the sky, and you can see the conditions, and it's actually an exciting expedition to go up there. And now we go to this room in Waimea. It's a different experience. It's still good, but it's different. Yeah. Yeah.
Could you talk a little bit about your discovery of the Kuiper Belt?
No. Oh, yeah. I will, yeah. So this is just the intro part. I think it's taking way too long. This is the intro part. I was going to talk about that and some other stuff right afterwards. Yeah, I'm just being facetious. Let me say these things. This is a quick overview. So we describe the solar system really as being divided into these three regions or domains now. So there's one called the terrestrial planet domain. It's the rocky planets, Mercury, Venus, Earth, Mars, and the asteroid belt. And maybe the moon is counted in that too. Then the giant planet domain is Jupiter, Saturn, Uranus, and Neptune. They're quite different from the Earth because unlike the Earth and Venus and so on, they're not made of rock, they're made mostly of gas. So the gas giant planets. And then the rest of it is well described as being cometary in nature. So these are small bodies that contain ice. They have a significant fraction of ice in their makeup. And we think of the solar system divided into these three regions. I just mention that because we have this kind of order of understanding or misunderstanding about them. The terrestrial planets are well understood because we live on one and we know a lot about the Earth and because we can reach the nearby terrestrial planets using spacecraft. The gas giant planets are much less well understood because they're further away and we have fewer ways to measure their properties, so we just don't understand what's happening with those planets so well. And the comets are almost completely mysterious because until recently they've been so small. The nuclei of comets are a few kilometers across, a few miles across. They're so small that we couldn't really measure any of their properties at all. So we have this kind of descending line here from things that we know quite a lot about to things that we know a little about to things that we really don't know much about at all. And then behind these words, I have a movie that shows what you would see if you were on a spacecraft that started near the sun, excuse me, and moved radially away from the sun at some high speed. So I'll just do that movie. I might do it twice depending on what happens. So here we go. There's the sun in the background. There is Mercury and Venus, and there's the Earth. There's Mars. Next up is Jupiter. We just passed the asteroid belt. You didn't see it because it's so small. There's Jupiter, the biggest planet, 300 times the mass of the Earth. Saturn with its rings, 100 times the mass of the Earth. Uranus. Next is Neptune, same size as Uranus, about 15 times the mass of the Earth. Then comes Pluto, yep, which is a binary. It's got a big satellite right there. And then we end this movie with some other big Kuiper Belt object out there. So I like that movie. It was made by the International Astronomical Union, and it's one of the few good things they've done. I like this movie because it gives you an idea of the empty nature of the solar system. So here comes Jupiter, 5 AUs from the sun. The Earth is 1 AU. Saturn is at 10. Uranus is about 20 AUs from the sun. Neptune is about 30. And look, there's nothing going by in these huge spaces between the planets. Pluto is now beyond 40. There it goes. And we have Kuiper Belt objects, which we'll talk about in just a moment, that go all the way out to beyond 1,000 AU. So space is really, really empty. There's just not a lot of stuff there. And that's one of the reasons it's very hard to study. So there are the terrestrial planets as imaged by various spacecraft. So those we won't discuss anymore because we know all about those. We think we know what they're like inside, and we think we know how they're formed. Here are the giant planets, mysteriously described in Chinese. This is for way in the front. This is Jupiter, as I said, 300 times the mass of the Earth. Saturn, with the spectacular rings, is 100 times the mass of the Earth. And these two guys, Uranus and Neptune, are about 15 times the mass of the Earth. And so these are quite different from the terrestrials in that they're made primarily of gas, mostly hydrogen and helium like the sun. And then by the time we get out to the comets, the pictures become less good. I have a couple in just a moment. We think the comets come from these two main places. The first one is called the Oort cloud, and this is a big spherical thing surrounding the sun. So the sun is the yellow point in the middle. This is a spherical swarm, like a big swarm of bees surrounding the sun. And it goes out roughly a third of the way to the nearest stars. So it's huge. And the amazing thing is it's so huge that we cannot directly see any of the objects in it. We can only see objects from the Oort cloud once they've been kicked out of the Oort cloud and they fall into the inner solar system. And when they do that, we call them long-period comets. So the existence of the Oort cloud is inferred from the appearance of long-period comets, orbital periods bigger than a couple hundred years. Then there's this Kuiper Belt, which is like a fat donut ring beyond Neptune. And in this diagram, which is too low probably for some of you at the back of the room, these things are the orbits of Jupiter, Saturn, Uranus, and Neptune. And then this thing out here, this big band, is the Kuiper Belt. So the comets come from these two regions. We think that the Kuiper Belt has always been there. We think that objects formed there and always have been there. We think that the Oort cloud comets formed close to the sun and were scattered out, were ejected out. So how do we find them? So to answer your question directly, we find these objects by looking for their movement. So this is not the first Kuiper Belt object, but it's one of the first. It's a sequence of pictures. This is a galaxy. Actually, all these things are galaxies in the background. This is a tiny, tiny piece of a huge CCD that, if I showed the whole thing, would cover much more than this room. And you can see this thing moving across. That's moving because it's moving in a circle around the sun. It's orbiting the sun. So we basically take a mini movie and look at the movie to see moving objects, and that's how we discovered the Kuiper Belt and many, many other cool things in the outer solar system. So this Kuiper Belt is significant because it explains where the short period comets come from. Comets with an orbit period less than a couple hundred years apparently fall into the planetary region from this Kuiper Belt ring beyond Neptune. And so it's kind of a complement to the Oort cloud, which supplies the long period comets. And then we care about the objects in the Kuiper Belt because they're very, very cold. They're so cold that they probably have trapped all sorts of interesting low temperature ices. So water ice for sure, carbon dioxide ice, carbon monoxide ice, conceivably nitrogen ice, frozen in these bodies 4.5 billion years ago when the solar system formed, and just kept there ever since. So we think of them like samples of the original material from which the solar system was formed. And that's why they're interesting. They get a lot of attention because they're somehow connected back to the very earliest times in the solar system. Pedro, the guy you saw in the movie just now, made this perspective view of the solar system. So again, the white circles are the orbits of the planets, Jupiter, Saturn, Uranus, Neptune, and these things are the somewhat inclined orbits of the Kuiper Belt objects that we know of. So we have 1,300 known Kuiper Belt objects at the present time, all of them found since 1992. And the message of that is when you find the first one, the other 1,299 are easy because you know they're there. But before you found the first one, you don't know if there's anything there, so it's really hard to find that. It's a big psychological battle in this field and many other fields. So it's a fat ring, a disk of bodies beyond Neptune. And it's the home of the comets. So we have a number of inferences from observations of the Kuiper Belt that have led to this model of the solar system. I'll just show you the model. It's a movie, so it's nice to look at. And I'll talk about it as it goes along. But the bottom line is it's a movie of the evolution of the solar system that tries to account for the existing structure of the solar system. Okay, it's called the Nice model because it was invented by a person in Nice, and most of the people who worked on this are in Nice in France. And you can call it the Nice model as well if you want to. And they want you to call it the Nice model because they think it's a nice model. But it's really the Nice model. So this involves two things that are important. First of all, we now know from the Kuiper Belt that the orbits of the planets have changed in size. So, right now, Neptune is 30 AUs from the sun. We know that it didn't form at 30 AUs from the sun. It formed much closer in, maybe at 20 AUs, maybe at 15 AUs from the sun, and it's drifted out. So that is called planetary migration, and the evidence for that comes directly from Kuiper Belt. And then we also know that if two bodies come into a resonance, and this is the most technical thing I'll mention, if two bodies come into a resonance, it has a strong effect. So a resonance is like the following. Imagine you're pushing a child on a swing. The swing has a natural frequency or natural period. So if you push in phase with the natural period, you wait till it comes up like that, and you give it a push, and it gets bigger, and then you push like that, and then you build up the amplitude of the swing by pushing in phase with the swing. That's called a resonance. If you do the opposite and you push randomly, so it's coming this way, and you give it a push then when it's coming towards you, some of your effort is wasted. So if you just push randomly on a swing, you don't build up a big oscillation, and your child is disappointed. If you push in phase with the swing, you build up a big amplitude, and you basically create a big shake, and your child is very happy about that. So the same is true for the solar system. If you have two planets whose orbital periods are in a resonance, then they can interact very strongly. And that means, for example, suppose you have one planet that takes 10 years to go around the sun and another one that takes 20 years to go around the sun. That would be called a 2-to-1 resonance because 20 divided by 10 is 2-to-1. And that means that the geometric arrangement of the planets repeats every 2 orbits of the fastest planet. So that idea, which is substantiated also by things that we see in Kuiper Belt, has produced this model. Here's the model. The axes don't matter too much, but you'll get the idea from what happens on this plot. So these are the planets, 1, 2, 3, 4, Jupiter, Saturn, Uranus, Neptune in here. And this is the Kuiper Belt, shown by a row of green dots right here. So what's going to happen is that when the model starts, the bodies begin orbiting the sun, and these bodies begin to interact with the planets, and the planets will throw them around. So the planets have a lot of mass. Kuiper Belt objects have not much mass. So if there's any interaction, the thing that gets thrown around is the Kuiper Belt objects. So it starts out like this in what is a very thin disk, and then it immediately gets puffed up into a very thick disk. This is a set of particles being launched up here in this direction, away from the sun. And you can see the planets are jumping around. That's because when a planet ejects another body from the Kuiper Belt, it recoils. Like if I push on this speaker, I don't want to do it. If I push on the speaker, if I push hard, I will bounce off in this direction. The speaker will go that way. So this goes on for a long time. It causes this complicated structure to appear in the Kuiper Belt. So this is the Kuiper Belt being puffed up and made fat in the outer parts. And the planets jump around because of this recoil. As they kick objects out of the solar system, they recoil in the opposite direction. Meanwhile, these two planets, Jupiter and Saturn, are drifting slowly towards a resonance, when their orbit periods will be in the ratio of 2 to 1. And when that happens in just a moment, the picture changes quite dramatically, like that. And so that results from this planet. Notice the planet's over here now. So this is Neptune at 30 AU. That's where it is now. Started over here, got chucked over there. So in this model, which may not be correct, of course, but in this model, interactions between the planets cause one of the planets to be thrown into the Kuiper Belt, shaking it up. And so it's like throwing a rock into a nest of hornets, basically. They may be peaceful at first, but the rock goes in and bang, off they go. So that NICE model is a nice one. It explains many features of the solar system, but doesn't make many predictions. So we don't know if it's a good model, but we know it's a pretty model. Here's the same thing in slow motion. That's the slow motion deal. So you can see, just do it one more time. It's kind of cool. Watch this planet. Here it goes. It's getting all jumpy, and then it's going over. And it's so massive, it just stirs up the Kuiper Belt tremendously. And then most of these objects are ejected from the solar system, and they drift among the stars forever. Many others come in and hit the planets and the sun and are so destroyed. So that's basically a state-of-the-art model of the solar system as we have it. We don't have any better ideas for the way things evolved in the solar system than that, although there are many doubts about this model, frankly.
What's your time frame in years?
Well, the time frame for the movie I just showed is 1 billion years from start to end, 1 billion years. But the time scale can be adjusted. It's a model, it's not real. So you can adjust the time scale. So you could do the whole thing 10 times faster or 10 times more slowly, or not do it at all by changing the parameters of the model. It's a big numerical calculation as a special body. It used to be the smallest, freakiest planet with the highest eccentricity, the highest inclination. It was the oddball planet that didn't really look like any of the others and was by far the smallest. And now we see it's completely typical as a member of the Kuiper Belt. So those of us who think about these things like to call it a Kuiper Belt object before we call it a planet. But there's no harm in calling it a planet if you want to. You know, big deal. It just doesn't help anything. So it's just a question of perspective. Here's what the comets look like close up. This is the nucleus of a comet. This is a famous one, Comet Halley. Here's another one less famous, showing you they have these strange surface morphologies with lots of craters, some formed by impact and some not. This is a moon of Saturn that some people think is captured from the Kuiper Belt at some early time. And here's a picture of some of the objects which have been discovered in the outer solar system in the last decade, mostly. Some, basically the same size. This guy, UB313, same size as Pluto. And there are no doubt bigger objects waiting to be discovered out there. So, any questions about this bit before I do the last bit? Yeah.
Is the Earth affected at all by the Kuiper Belt objects, and is the orbit changing and drifting?
So that's a very good question. In this model, the Earth at first was not considered. So this model was produced in 2005, basically in response to Kuiper Belt observations. In the model, the Earth was not addressed at all. More recently, it has been injected back into the model. So the Earth is such a small mass compared to the giant planets, it doesn't affect their evolution. But the reverse is not true. So the Earth is affected by the giant planets as they migrate around, especially when they go through the 2-to-1 mean motion resonance. So in the models that were published until very recently, the Earth was found to be unstable, meaning that its orbit didn't survive. So we would not be here if that was the correct model of the solar system, which the modelers, for some reason, see as a little bit of a problem with their model. And so they've adjusted their model so that that doesn't happen, which I would do too. Yeah, it's on the ball. Yeah.
Describe your identification of ice. We think of it as H2O.
That's water ice, but they're meant. That's water. Well, an ice is the solid form of a gas, basically. So you could freeze the air, for example, and if you froze the air, the whole atmosphere would collapse down to a layer, about that thick. Most of it would be nitrogen, 70% nitrogen. So that would be nitrogen ice. It would be solid, just like water ice, solid nitrogen ice. And there would be, 20% oxygen ice there too, and some CO2, carbon dioxide ice, carbon monoxide ice, would be argon. 1% of the atmosphere is argon. So basically, ice is a frozen gas. And at these very low temperatures, you can freeze all sorts of stuff that in the terrestrial environment are gas, but out there, they're frozen solid. Yeah. Yes. And then.
Is it true that the Earth just shifted on its axis a little bit? Do you have to change your measurements constantly, or is there something with that at all? Is that true?
The question was, is it true that the Earth changed its axis recently? And that's true. You mean because of the earthquake? Yeah, it did. But the Earth changes its axis all the time for all sorts of reasons. So it changes because the continental plates are moving around over the surface, and that changes the moment of inertia of the Earth and changes the spin. It changes for seasonal reasons. It changes because the temperature on the surface of the Earth changes, and so the ocean expands more over here than over there as a result of thermal effects. In principle, if everybody in the world jumped 2 feet to the right, the Earth would have to recoil in the opposite direction, so you could change the spin of the Earth's axis that way. So at some level, and many of these things are tiny effects but measurable, the Earth's axis changes all the time. Yeah, so it's got polar wander and wobble and shaking. Yes?
You think it's going to flip soon?
I hope the Earth doesn't flip. But you mean the magnetic field? The magnetic field's a different deal. Yeah, that might flip, but I don't know when that will happen. Nobody does. So it's chaotic, and the time scale is long.
In the waters are changing temperatures.
Yeah, but there's no detailed understanding of how that happens. In fact, there's no detailed understanding of how the Earth's field is generated. So that it's a bit like a dynamo. We send a current through a wire, and it generates a field. But where's the wire? I mean, the wire is the whole Earth's core, this metallic core. And so the question is, how do currents pass through the metallic core of the Earth? And that's a very messy thing to understand. So people work on that. It's a research topic, and there's no good understanding. Even making a dynamo that reverses with this kind of timescale is a tough thing. Yeah. So it could happen, but there's nothing we can say about that. And was there a question back there? Yeah.
You said that some of the bigger planets are made of different kinds of gases, and then outer belts are made of frozen. How do you know what they're made of?
So we take a spectrum. So spectrum means you take the light and you disperse it, for example, by passing it through a prism to make a rainbow. And then you look at the amount of red light compared to the amount of blue light, for example, or you look in detail and you see the spectrum is cut by black lines that are caused by particular materials. So you take a spectrum, you get a telescope, you put a prism behind the telescope, and then you take a picture of the spectrum coming through the telescope and the prism. And then you compare that with the spectra of things that you know. So you can take a spectrum of a bucket of water or carbon dioxide gas or whatever you want, and you look for these lines that are characteristic of each material. Yeah. So spectroscopy is a big field. Spectroscopy, a lot of people do that. It's a very interesting but difficult thing to do. Any more? Didn't want to go too long with this talk. I'll just go quickly through the last bit. Yeah, one more.
Do black holes operate at all in this area of the universe?
Not as far as we know. So the caveat to that is that in principle you could have very, very tiny black holes. Like even in this room, you could have very tiny black holes that wouldn't be very massive, and so they'd be hard to measure. And again, space is very big. Even in the solar system, there's lots of empty space and lots of room. And so conceivably, you could put tiny black holes into the solar system. But A, no particular reason to think that they're there, and B, no evidence that they're there whatsoever. Yeah. Okay, origin of the oceans. Just talk about that. So there is this question of where did the Earth get its water? And it seems like such a dumb question. You know, why would you even ask that? You know, it's wet. The Earth is wet. It rains, like just now. There are lakes. There's all this water is everywhere. But the problem is that the Earth formed very hot. So it was more than 1,000 degrees when it formed, and it was molten. It was so hot that the rocks were actually liquefied. And it was what's called a magma ocean covered the surface of the Earth, probably for the first 100 million years or so. And that hot magma is not very good at trapping water from this disk of material surrounding the sun. So people have come to believe that the water was added after the Earth cooled down. And it probably took 100 million years or something to cool down. So there's some way of adding the water afterwards. Now people have known for a long time that the comets are icy, that they contain a lot of water ice in particular. And so people said, well, you know, it must be the comets hit the Earth. There's a lot of comets flying around. They struck the Earth, and then they melted, and they made the oceans and all the rest of it. And that's still plausible at some level. So comets probably did contribute some of the water that we see on the Earth. But there are compositional differences between the water that's been measured in comets and the water that we measure in the oceans that suggest that comets are not the only source. So in the last 10 years, people have begun to look for other places where the Earth could have accumulated water. And it turns out that the asteroid belt, the outer parts of the asteroid belt, which is this ring between Mars and Jupiter. Mars is at 1.6 AU from the sun, 1.6 times the Earth's distance, and Jupiter is at 5 times the Earth's distance. That tiny ring of material actually is a pretty good source for water ice, at least potentially, for the young Earth. So this last part of the talk, most of which I'll skip over, really addresses that. We discovered a population of comets in the asteroid belt. So until recently, people thought asteroids are just as rocky as, you know, the rocks that you would pick up in your garden. They're not made of ice. That's crazy. They're just rocks. And so when you look at them, they just look like a little point of light. They don't look like a comet. They don't have a tail or an atmosphere, nothing like that. So we discovered this new class of object in 2005, 2006. And by sheer coincidence, I have a video of the moment of discovery. And the moment of discovery concerns me again at the Keck telescope with my grad student, Henry Shea, who has since gone on to bigger and better things. But here's the movie showing the moment of discovery of what we think are the parent objects for the Earth's oceans. Okay, so I'll just set this up. So it's the same room you saw before from a different angle. These are all computers that we use to look at the telescope and look at the instruments. You can see the time. It's about 5:35 in the morning, so we're just waiting for the sky to begin to get bright. And there's Henry taking notes as the data comes in from the telescope. And so you can see the moment of discovery is coming up in just a few moments.
Nothing's gonna happen.
Okay, right there was the moment of discovery. So that's what it's like. So that's actually true. But of course, you don't know that you've made a discovery until later because you don't look in enough detail to know when you've made it. It's not a blinding flash of light. It's something that you dig out through hard work later on. But that's what it's like. So that's as exciting as it gets at the telescope. So here's one of the objects that we were looking at. This is what's called a main belt comet. It's an asteroid that probably contains water ice. And so even though it's an asteroid, it looks like a comet. Here's another one right here. Yeah? So instead of being a point, which is what an asteroid would look like, it's got a tail, and it's basically a cometary object. And so these things are located in this yellow band between Mars and Jupiter, where everything else is an asteroid. So we think that these are probably parent bodies that have delivered water to the Earth, probably at some very early time. Now, people who study meteorites already knew that the meteorites contain evidence for liquid water in the past. So here is a cross-section. This is a cut through a tiny sample of a meteorite that came from the outer asteroid belt. And it contains minerals. This thing, SERP, is serpentine. That's a mineral that requires liquid water to form. So we know that there was in the past liquid water in these rocky asteroids in the outer belt. But what we found is ice in the asteroid belt now. So it's kind of a slightly different thing. And it gives rise to this idea that the asteroids were wet, and if you have water in contact with rock, there's a chemical reaction between, on long time scales, if you wait long enough, there's a chemical reaction between water and rock that produces new minerals like serpentine and other things and releases energy. And so this chemical reaction between water and rock is called serpentinization. And it sounds, it's a very fancy name, it sounds mysterious. But those of you who have mixed concrete know that when you mix concrete, which is basically a mineral, with water to make a hydrated mineral that is concrete, it releases energy, and the concrete, in fact, can become very hot. So it's exactly the same process that happens inside the Earth. We think it's happening here at this mid-sea vent to produce the energy that comes out in this hot water. The power of this thing is about 10 megawatts, and it's produced by serpentinization reactions under the Earth, not by heat leaking out, but by heat produced by a chemical reaction. So this probably happened also in the asteroid belt, inside the asteroids. So we suddenly see that the asteroids have gone from being dead rocks to being interesting places where there's chemistry and heat and water and all sorts of goodies going on. Let me just tell you this story and then I'll quit. This is a meteorite that fell in Texas in a place called Mauna Kea. So it's called the Mauna Kea chondrite. And the Mauna Kea chondrite is very special, not because it fell in Texas, but because it fell near some teenagers playing basketball in Texas who were very observant teenagers who noticed this thing fall and who stopped their game of basketball, figuring that this might be more interesting, and ran over to the meteorite and picked it up inside a plastic bag immediately. Within a minute of the fall, they picked it up. It was still warm to the touch. And so that's good by itself, because they picked it up and they protected it in the plastic bag. The typical thing is somebody will pick up a meteorite and then it gets contaminated with the oil from the fingers and the water and the breath and the whole thing. They put it in a plastic bag and sealed it. But then they're absolutely brilliant. They sent it to Johnson Space Flight Center in Texas, and it got there 2 days later. And it was analyzed by one of the world's best meteorite experts. His name is Zelensky. And Zelensky hit it with a hammer and chipped off this piece right here. So you can see a black fusion crust, and then inside is relatively light material. And then he took a microscope and looked at this white surface. And what he saw is shown in the blue circle at the upper left. So the meteorite down here is about 4 inches across. This field of view is about 1 millimeter, 25th of an inch up here. And inside there, it's not very clear in this projection, but inside here is a square thing, which is actually a cube. And if you think back to a recent meal, you might remember something that you can eat, which has a cubical structure to it, and it's called salt. Sodium chloride, salt crystals, are little cubes. So it turns out that this is a cube of salt. And the age of this cube of salt has been measured by radioactive decay dating. It's a standard technique, and it gives an age which is 4.7 billion years. So it's as old as the solar system. So this is salt, a salt crystal that grew at the beginning of the solar system inside this meteorite. And the guy told me this story a few weeks ago to check that he'd really found salt. He said, I had to do what all good geologists would do. He licked it. So he licked he licked the meteorite and tasted this cosmic salt from the beginning of solar system time, which is pretty cool. Then, if you look inside the salt crystal, there are little dark things here. Here's one shown close up. This is a small pocket full of liquid salty water, brine. This is very small. It's 5 microns, 5/1000ths of a millimeter. So that's a brine pocket. And this, inside the brine pocket is this thing called V, which is a tiny, tiny bubble. And Zelensky said, you know, if you tip the meteorite upside down, you can see the bubble floats up to the top. And if you tip it upside down again, it goes back up to the other top and so on. So it's really a bubble inside a liquid brine pocket, inside a salt crystal, inside a meteorite that was part of an asteroid in the outer asteroid belt that got smashed, and then the fragments were delivered to the Earth by some process. So all of that's kind of fantastic, I think. And then under the microscope, if you look at that carefully, you can see that it moves all the time because it's being hit by molecules from the water, from the brine around it, liquid water, and it's constantly vibrating and shaking. And so he sent me this movie that he took through a microscope, which is really hard to see, but there, if you look there, you can see a small black thing. The small black thing is the bubble. Yeah, you can see it vibrating, moving around. And basically, it's been doing that for billions of years inside that little tiny brine pocket, just vibrating around, just doing that forever. So how do you get salt crystals in a meteorite? You start out with water. The water soaks up minerals, just like on the Earth, soaks up minerals from the rocks. Then the water evaporates. And the more it evaporates, the saltier the water gets. And then you get brine, like in the Dead Sea or somewhere like that on the Earth. And then eventually you have salt crystals sitting in brine. Then those were captured inside this meteorite somehow. So it's perfect proof of the past existence of liquid water, probably lakes inside these tiny asteroids in the outer asteroid belt. So I think that's all pretty fantastic stuff. But then the last thing I'll say is even more fantastic. So think about, on the Earth, what happens when you have heat and water and rocks. Where would you find such things? Well, you might think of the mid-ocean ridges of the Earth. So these are places where there's heat coming out from the interior of the Earth, causes the ocean to become very hot. There are lots of minerals dissolved in the water. What you get are these giant chimneys growing above the vents in the center of the ocean, and what you get is a vast abundance of life growing at these vents. And there's wide speculation that some of the most primitive, maybe the first significant organisms on the Earth, appeared at places like that, mid-ocean ridges, where you have this combination of water and energy, heat, no light, but because it's so deep, but heat and minerals. So bugs could evolve and grow and eat stuff down at great depth. So all of those ingredients actually probably occurred in asteroids in the outer part of the asteroid belt. So it leads to the following picture, which may not be true either, but it's consistent with most of what we know, in fact, with everything we know. The idea is that the asteroid belt, because it has many, many, many asteroids, provides many, 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 many experiments, different locations with slightly different values of temperature and density and pressure and composition. And so each asteroid you can think of as a separate chemical experiment in which life might get going or might not, depending on what happens. So in the asteroid belt, there are 50,000 possible places where life could begin at a time when the Earth was too hot for life to begin, because the Earth formed molten and it took 100 million years to not be molten, and you probably can't start life on molten rock. So the asteroids initially were a better place for this early prebiotic chemistry to occur than was the Earth. Even better than that, we know that the asteroid belt initially was much more massive than it is now. So basically, the asteroid belt was disturbed by the appearance of Jupiter, which scattered many bodies from the asteroid belt and sent them hurtling through the solar system. So if life started in the asteroid belt, it would be dispersed through the solar system by the formation of Jupiter, and life-bearing asteroids would be scattered everywhere. So the ones that hit Mercury would do nothing, because Mercury is hot, has no atmosphere, they would die. The ones that hit Venus, likewise. Venus is too hot, they would die. the ones that hit the Earth and Mars would survive because Mars probably had a good climate for some of its first few 100 million years, first billion years. But eventually they too probably died because the climate now is not very good for life on Mars. So in this picture, you can think of yourselves as possibly basically children of outer belt asteroids. That the precursors to life actually began in the asteroid belt and were spread through a dynamical process through the inner solar system. So we don't know if that's true. That may not be true, but the evidence does not contradict that in any way. So it's a measure of how little we know about the origin of life and early conditions in the solar system, that could be true. So that's a really nice idea and really something that needs to be tested by future measurements. So I'm just going to stop there because I talked for too long already. Did you have any comments or questions about that? Yeah. Yeah, because we know, roughly we know how much, well, we know how much water there is on the surface of the Earth. It's about roughly 1/100% of the mass of the Earth. So we know the mass of the oceans and the mass that's absorbed in plants and so on. The question is, how much more water is buried beneath the surface of the Earth? So we know that water can be combined in minerals that then get subducted beneath the surface and taken into the mantle. And so we don't really know how wet the mantle is, but experts, and I'm certainly not an expert, think that maybe you can bury another 1 or 2 oceans of water in the mantle. And then there's another question, how much water could you sink into the Earth's core? So the Earth's core is 3,000 kilometers, 2,000 miles down. It's mostly iron and nickel, but actually it's kind of a sponge, and you could, in principle, dissolve other things. People think there's sulfur in the core, but there may be oxygen from water or hydrogen from water in the core too. And if that's the case, then you could put a very large number of oceans into the Earth's core and have no visible trace of that to us on the surface. So the answer is kind of limited by our ignorance about the total water abundance. But if you just take the oceans on the Earth, then I seem to recall that you need either a single body equivalent to 400 kilometers in diameter or a larger number of smaller bodies to supply the ocean, something like that. So it's more water than exists now in the asteroid belt. But the asteroid belt is a remnant from a more massive belt, so it's still plausible. Did that answer your question? Aha. So what was it? Say it again then. So maybe I misunderstood. Low number of what?
I'm trying to conceptualize if each one of these asteroids is a little dump truck delivering its thimble full of water.
Yeah.
Were they deposited by result of impact on the Earth?
Yeah.
So how many impacts of how many of these asteroids?
Oh, it depends how big they are. So what I tried to say, but apparently not very well, is that just in terms of the mass of water, if you had a single sphere, a single asteroid made of completely of water, 400 kilometers across, that would supply the Earth's water in one shot. It's very unlikely that we had such a single big impact. It's much more likely you have a rain of smaller bodies coming in. So it just goes, you know, if they're 10 times smaller, you need 1,000 times the number. I don't know who was next, but...
Dare I ask, while you're in the Bible Belt, do you see a higher power in all this beauty
No.
that you're talking about?
No, I don't. I definitely don't. No.
Just curious.
You're welcome. I like to be blunt. Yeah.
Thank you.
Yes.
If life originated in the asteroids,
Yeah.
presumably we should be able to somehow, by looking hard enough, find some nucleotides in the asteroid.
Right. Good. Yeah.
And is that being pursued? Is there any
Well,
evidence?
yeah. So you could be even more bold and say, you know, if life started in the asteroids, maybe we can find fossils in the asteroids. Maybe you can look at meteorites and see little fossil skeletons of things that evolved in the asteroids. So people have looked. The trouble is most of the samples that have been looked at have been cooked to a level where the evidence would be destroyed. You know, even on the Earth, the earliest evidence for life is equivocal. So when you go before about 3 billion years, you see little things, and they look like they might be cells, but maybe they're not. Maybe they're produced by some other process. And so it becomes ambiguous as you go back. That same problem is replicated for the meteorites. Chemically, we know that the meteorites deliver certain hydrocarbons. They're kind of tarry substances that contain lots of the things you need for life. So the precursor molecules, there are ring molecules and chain molecules. So it's in the right direction, but in terms of finding specific fossil evidence for life, either with immediate precursors to DNA, no, not yet. But I think the door is still open, and if people are motivated, they'll look harder. I don't actually know who's first or how to decide who's first. Sorry, please go ahead. Yeah, would you like to go ahead? Okay. Yeah.
I want to know where your thrill comes from in science, because you impressed us how it might be a boring thing to watch people doing astronomy, but I know there's a kick, there's a thrill, there's something there that keeps you doing it, and I'd like you to talk about that.
So, the motivation is actually, when I grew up, people told me, by implication, people gave me the impression. I grew up in England, right, in this actually quite good educational system for young people. It gave me a very wrong impression about the world and about what's known. So I picked up from my teachers the idea that basically everything is known, and that, you can spend your whole life until you get to the edge of knowledge trying to learn things that have already been figured out. But then when I was 10 or 12 or something like that, I began to realize that's absolutely not true, and that as a child you can ask questions to which there is no answer. And so that for me was a big discovery. It's like, whoa, how could that possibly be true? People have been doing this for hundreds of years or thousands of years, but we only got this far? What's that about? So then suddenly I realized that instead of this boring thing of sitting down reading books about, oh yeah, somebody discovered this, now we know that's true and all this, it suddenly became much more interactive and exciting because I could do something. I can do a measurement that actually may reveal a new thing. So that still is my excitement. Yeah, I mean, I still like the idea that I can go out and find something that nobody has ever seen before, or perceive, more important, perceive something that nobody ever perceived before.
And you have done that.
Like
Yeah,
the
yeah, yeah.
asteroids. Would you talk about your X and the asteroids just
Ooh.
for a second?
Yeah, I have that elsewhere, but
Okay.
I mean,
Just discovered that. That's fascinating.
well, actually, it was discovered by somebody else who didn't know what it was. So,
The card said you did it.
what?
The invitation tonight said you did it.
Well, I realized what it was, but other people discovered the object and misclassified it, which has happened many, many times. Let me just get a picture of that. So it's so this is a body. Okay, here's the object. So this is an asteroid. This object was reported by a U.S. Air Force telescope. So there's a telescope that surveys the sky looking for basically bad things like enemy satellites and bombs and stuff in space. But it also finds natural objects like asteroids and comets as well. And then when they do, they tend to report them to the IAU, the International Astronomical Union. So they reported this object as just a regular comet. But so that was the discovery. They reported it as a comet. But I looked at the orbit and I realized immediately that it's an asteroid. So these numbers at the bottom tell you very clearly from where it is and the inclination and the eccentricity tell you that it's not a comet, it's an asteroid. So based on that, I started thinking about how to get a quick look at this. And I realized that this person, Jim Annis, who used to be a graduate student with whom I wrote a paper a long time ago, was observing in Arizona on Kitt Peak. So I sent him an email just as he was starting to open the telescope, and said, maybe you could just take a look at this interesting object because it might be really, really exciting. And so I got him convinced that this is worth his precious telescope time. So he took these two pictures. So the things dancing backwards and forwards are stars, and this object, which is an asteroid, but it looks like a comet, is the thing behind. And then in this picture, I noticed that at the front end is like a little nose, a snout sticking out, which is unlike anything I've seen before in a comet. So I was able to get more images, better images that look like this. So you see this trail of dust, but you can see this little snout thing sticking out of the front, which is just weird. It's just not something that's been observed before. So this is like a cascade of opportunity. First of all, it's a random discovery, but then it's not what the person said it was, and then it looks different from anything that I've seen before, and then it still looks different from anything that I've seen or anybody's seen before. So then we go all the way to the Space Telescope, and we get this picture, which shows this point source, which is a 140-meter rock or nucleus. We don't know what it's made of. Followed by this tail of dust, but in the tail of dust are these like scratch marks. So these are X-shaped marks and other things in the coma of this object, which have not been seen before. So we don't know yet what that is, but my best guess is that this is a collision between two asteroids. And these are sheets of debris. You know, if you throw a rock into a swimming pool, the splash comes out. The splash is not a uniform cone. It comes out in sheets and jets. So these, in my mind at least, are the sheets and jets of ejecta from an impact between two asteroids. So that, if that's true, and we're taking more and more measurements to try to prove that or disprove that, if that's true, it's the first time that collision between two asteroids has been observed.
And you observed it. Good for you.
Yeah. And so it's interesting because it opens this this process. I mean, collisions must happen all the time at some level, but until now we've never seen one. So we have to simulate them with calculations in a computer. It's not so good, or try to do them on a very small scale in the lab, literally on this scale. You know, a little pea-sized thing would shoot into a target in a vacuum chamber, and it's just not so good. So if we can see one happening on a cosmic scale, a natural scale, we can learn much more. Well, it's a comet by the operational definition. A comet just means hairy star, and so that does have hair. But the orbit is the orbit of an asteroid, so it's both a comet and an asteroid.
The core is not inside the...
Yeah, I know, the nucleus is outside, yeah. So it's true, I'd like to do this kind of thing because it's new and it's cool. And I try not to do the same thing too much. I mean, we all do the same thing over and over again, because once you can do it again. But I try not to get into that mode too much. So this is a little bit different from other things.
How many papers are under your belt?
I don't know, 100 and something, I don't know. Yeah,
So in all that,
200, I'm not sure.
you find any extraterrestrial life then, huh?
I'm sorry?
As far as UFOs and all that, you've never seen it, you can put it to rest, like that stuff doesn't exist out there. Like SETA, are they wasting their time with all the years
Is-
and things that you've...
Are SETI people wasting their time?
Yeah.
No, definitely not. So that's very exciting for me. That's very, very interesting. They should get much more money to do a much better search, because finding evidence for, okay, there's two things. Finding evidence for life, you know, maybe we get a meteorite with a bacterial cell in it. That's really cool. That's really interesting. Or maybe we get a Mars sample with some ancient fungus fossil or something in it. It's also really cool and really interesting. But best of all would be to get some intelligent signal from elsewhere. So there haven't been many experiments dedicated to that, very few really, with any sensitivity in the radio or the optical or anything. I think that would be a very, very good thing to put a lot of funds into now. And there are people who would do that. In fact, I'm going to this SETI Institute next week to talk to those people about some other stuff. But for political reasons, their funding actually was cut. So they used to be supported by NASA, and then a certain congressman whose name I've forgotten decided that this is the most ridiculous thing in the world, and you know, why should the federal government ever be supporting the search for a little green man? And so NASA, in its political sensitivity, said, oh, we're not, and they cut the funding. So it's really the reverse. You know, if you don't look for something, you'll never find it. That's certainly true. And if you don't know what you're looking for at some level, you'll never find it either. But we do have an idea of what to look for in terms of extraterrestrial signals.
Thank you.
Yeah.
I think it's clear the questions could go forever. And you're a great audience, and Dave's been a great speaker. I think we ought to end it here, though. Dave, I think, will be around for a few more minutes, and people could individually ask him questions. Let's thank Dave for his wonderful.